Okay, hello everybody. Hello. 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 See you guys. Hello, 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 hello. This is the part where you stop talking and I talk instead because the lecturer and students, cool. Hello everybody. Welcome to an exciting, yet another exciting COMP1511 lecture. Sorry it took so long to get set up. I couldn't load VLab, and then I tried a different port and I could load VLab, so I don't know, VLab's fantastic though. So whatever, lecture 21, Wednesday, week 12. We're going to be looking at some cool stuff today. Analysis, sorting, and searching. That will mean more momentarily. Some quick admin stuff. This is basically the same as it was yesterday, except that the solutions are now out for the week 11 lab. So if you aren't really sure how to start on the assignment or you didn't get them working, take those solutions, and that's like your starting point for the assignment. So those are out now. You can look at them now. And there will be lectures next week. So I know that your timetable says there's not one on Tuesday, but there is one on Wednesday. There will be one on both days. So there will be one here Tuesday next week, Wednesday next week. Cool, so I did the questions thing yesterday. I hope it was helpful to those people whose questions I could answer. But looking through the questions afterwards, I was sort of like, these should be posted on Ed. So if you have any questions that don't get answered, or if you posted a question and I didn't answer it, you should go to Ed. Is this going to work? It's going to work. This is exciting. Come on. Maybe. You should go to the fantastic and totally not slow Ed. Also, ask your question in here, put some words in here, and then me or any of the other fantastic people will answer your questions. So to those of you who asked really good questions yesterday, which was everybody apart from the people who said hello world, like 3 people just said hello world as a question. That's, I don't know how to answer that. But ask your questions here. Otherwise, I've made another questiony thing for today's lecture if you want to ask questions there, which we may or may not have time to answer. So, thinking about this course, right? In this course, our goal is to get you thinking like a programmer. So our goal is that by the end of the course, you are a competent programmer. You can solve problems by writing programs, and you can sort of express yourself in the C language. And you might be thinking like, yeah, cool, awesome, I can write C code, I'm a programmer, this is everything I ever need to do. But we have more comp courses for a reason. And in future comp courses, particularly COMP1521, we get you to think like a computer scientist. So not just like, look, I can write code, my code works, but is my code effective? You know, what should I be doing with my code? That sort of thing. So today we'll have sort of a taster of this. You should take COMP1521 for more. Fantastic course. Hang on. Okay, I just have 10 blank slides. That's fine. I'll go with that. Oh, hang on. What? Those were fantastic slides. Where did they go? I loved those slides. Sorry. Let me just fix this. What has happened? I didn't close. Yes, see, there was a fantastic slide. So what happened there? How many of you know like HTML programming or anything sort of like, that's a very small number. So I write my tags in sort of HTML and I forgot to close one of my slide tags. So I didn't get any slides. Cool, so we've looked at, you know, my code works, yay, my code compiles, it passes the auto tests, this is good, everything is perfect, right? But sometimes it works isn't good enough. Like, just because your code works, gets the right answer doesn't mean that it's actually going to be useful. So let's think, like, what makes software good? I thought of 4 things. Maybe you can think of some. The first one I've sort of mentioned already is it works. It's good if it works. It's good if it's correct. But what else makes software good? Yeah? It's easy to use. Yes, hold that thought until point number 4. What else? Yeah. it serves its purpose, it does what it needs to do. Yes, it does something useful, yes. I've sort of already hinted at like analysis efficiency. Software is good if it's correct, but also if it's efficient, right? Another really important thing that you will come to appreciate more in future years as you work with other people's code more is code that's clean, easy to understand, easy to maintain. If you think about I'm sure at least some of you wrote really horrible assignment solutions and you just wanted to get it working and it was all, by the end it was like spaghetti, and you don't want to have to maintain someone else's code that they've written that's like that. So, and you can totally see that down the bottom. Yeah, software that you can use is also really important. But for today, we're just going to look at efficiency. So, there we go. Correct is important, but efficiency is also important. So we often need to consider how long something takes to run and how much memory it uses. Those are sort of two of the things that we can measure. A program that's correct but too slow can be useless. Like if your program is designed to do anything at all and it takes 1,000,000 years to run, that's not very useful. In terms of how efficient something is, it often depends on the size of the data that's being processed. And if we can work out how this changes, so how changing the data, the amount of data will change, how long it takes to run, we can predict what it will be like on larger and larger data. If you think about it, in somewhere like Google, right, where they have 1 zillion user Google searches per second, that sort of thing, they need to be able to go, I've written this code and I can tell based on the stuff I've done here that when it has a gazillion things in it, it'll be fast enough. If you're just going to hope that it's fast enough and then try it on a gazillion things and see, I mean, if it's not fast enough, then you've just broken Google. So not a good day for you. And so being able to extrapolate, I guess, from smaller inputs, how efficient things will be in a Y scale is very useful. And much more on this in COMP1511 and 18s1. So in terms of finding out whether a program is efficient, we can take an empirical approach. We can just run the program, right, lots of times and measure how long it takes. So if we give your fruit bot, for example, a world that's got 10 things in it and then time how long that takes, 100 things in it, 1,000,000 things in it, and time how long it takes each time. And we can sort of extrapolate from that how long is it going to take as the numbers get bigger, assuming that it's like deterministic. Or we can take a more theoretical approach where we try and actually work out the number of operations that are taken on an input of size n. We refer to n a lot in computing as sort of like the number of things or the size of the inputs. So if I was giving you a fruitbot world that had 1,000,000 places, I would say that n is 1,000,000. N just refers to the number of the size, I guess. Cool, that is totally unreadable. Is that font too small or is that okay? Is that okay? Too small? Because if I zoom in, this happens. Oh well, the last parameter is int x. It's slightly cut off. So one example of, I guess, the complexity of something, an example of how the time something takes can change as it gets bigger. If you imagine we're trying to search through an array. So we have an array with some number of things in it, and we want to see if a given value is in that array. I guess the obvious way to do it is to just look through the whole array, right? Is it in this element? Is it in this element? Is it in this one? Like, no. Oh, yes, I found it here, so it's in the array. Oh yeah, that's literally what I just said. So I guess doing an informal analysis of how long will this take. We start at the first element, we look at each element as we go along, and we stop when we find the element or when we hit the end. So if there are n elements to search for, in the best case we check one thing, right? In the best case it's the first thing we look at. In the worst case it's not on there, so we look through all of the things. And on average we would have to check half of the things. So if you think about it, like the probability of it being at any given point is such that if we have to look through all of the things, I'm not describing this very well. On average, we will find it about halfway through. Or on average, if we're looking for all of the things in the array, do you know what I'm trying to say? Yes? No? Hopefully. That was not well explained at all. But yeah, on average, if you're looking for something in the array, you'll have to look through about half of the things. Sometimes you have to look through all of them, sometimes you have to look through like just the first one, and so on average. Cool, and so this is good, except this is not good if we have a lot of things to search through, right? Like, can you think of something that you'd have to do where you're asking a system for something and it's got to like read through every single other entry in the system? What about like, is the enrollment system still really slow? Yes, yes, one person's nodding. I think the special consideration system is worse. So I don't know if any of you have had to apply for special consideration, but students and then lecturers, if they're looking at them, like you go, show me the special consideration request. So people have been sick and wanted an extension on something. And the page takes about several minutes to search, and then it finds the one person who had the thing for COMP1511. So maybe what they're doing there is they're actually looking through every single request they've ever had until they find one that matches. I hope they're not doing that, but when it takes several minutes to find one thing, it sort of feels that way. And so this gets really bad if you have lots and lots and lots of things to search through, because you'll have to search through half of them on average each time, right? But if we have 50,000 UNSW students, then I'll have to look at 25,000 things on average to find your ZID, maybe if they're not in order. So how could we improve this? Is there anything you can think of that we could do that would make it better than having to look through every single thing?
Use a tree.
Use a tree? What is a tree? It's like a thing that grows in the ground. How could a tree help you find things? I don't know, maybe you'll find out in COMP1511. So let me get some code, I think. Okay, there we go. Okay, VLab hasn't crashed. If VLab crashed on me, I would cry. Not literally, I hope. I forgot to make the directory link. Come on. Wednesday. Okay, there's a folder. It will have code in it. Cool, okay, the code is there. I was really hoping this would be fast. So let's say we have an array that's 10 big. Is that all of the numbers? 1, 2, 3, what have I forgotten? 6? That's roughly 10. Cool, so I have my array, and I have my function. I think I heard someone say it's the first time he's used a for loop. It's Andrew Taylor's code. That's why there's for loops. Okay, function prototype. Okay. Okay, cool. My code, it works. It works. Everything is great. So I've wrapped a main function around this. I tell it, like it scans a number from me, and then it says whether it's in the array or not in the array. Right, so if I look for the number 5, 5 is in the array. If I look for the number 20, 20 is not in the array. Cool. So I'm going to get it to print out the one that it's currently looking at so that we can see as it goes through, come on, which ones it's looking at. Cool, so if I search for the number 10, it looks at 3, it looks at 1, it looks at 4, it looks at all of them, it gets to the very end, and then it goes, it's not on the array. If I tell it the number 1, right, it'll look at the 3, it'll look at the 1, and then it'll go, cool, I found one, it's in the array. So if we've looked at the 3, like, so we're looking at our array, right? We're trying to see if the 1's in there. If we're looking at the 3, does this tell us whether or not the 1 is in there? Like, all we know is that it's not in that spot, right? Because it's a 3, not a 1. And then when I get to this 1 here, oh, I found the 1. It's the one, it's the number I'm looking for. Is there any way that we could change it so that it can look at the number and then from that get some information about whether it should keep looking or give up? I don't know if I hinted at that very well. What if I could look at this 3 and then know that this rules out, like the fact that there's a 3 here means there's not going to be any numbers of some other kind. Let me give away what I'm trying to find. What if we sorted the array? So what if we had it in order? So it was 1, 2, 3, 4, 5, 6, 7, 8, 9, for example. If we're looking for the number 10, we can go, sure, 10's bigger than 1, so keep looking and so on. But if we're looking for the number 0, when we hit the number 1, we can go, oh, I found 1, we know 0's not going to be in there. Does that make any sense? Why are you so slow? So, does what I'm trying to say make sense? I think I've left a pen for this somewhere. Did I put it in here? Cool. Is that readable at all? No, it's really not. Cool. Is that readable? Hopefully. So if we have our array, our numbers 3, 1, 4, 5, 9, for example, we've got to look at every single number here to know whether we've actually found the number we're looking for. Like if we're looking for the number 10, looking at this 3 doesn't actually tell us whether or not there's a 10 here. It just tells us that the 3 is not the 10, right? So we've got to look at every single thing. But if we had it sorted, so if it was like 1, 3, 4, 5, 9, if it was in the ascending order, if I'm looking for the number 0, for example, I can go, I found the number 1 here, and 0 is smaller than 1, so I know that it's not going to be in this array. Does that make sense conceptually? If you know that the array is in sorted order, so is in order where it goes smallest through the biggest, and you find a thing that's, you're looking for a value that's smaller than the value that you found, you know that the value you want isn't going to be in the array. Who is confused by what I'm talking about? Who is not confused by what I'm talking about and is paying attention? Okay, the rest of you, I can't help you if I don't know what's going wrong. So yeah, looking at this code here, for example, or looking at this example, if I wanted to see whether the number 6 was in the array, I'd look, 6 could still be here because 1's smaller than 6, 3 could still be here, 4, 5, 9. I'd get to the 9 and I'd go, I found a 9, and so I know that the 6 isn't in here because I hadn't found the 6 so far, and now this is bigger than the 6. Cool, does that make sense? How could we code that? We'd need to make a slight change to this code here. What this code does is it looks at every single array element, and if it's equal to that element, it's found it, and if it's not equal to that element, it keeps on looking. But instead, if I make it be a sorted linear search, array, what is going on? Right, so if my array is in order, the smallest one is in like array element 0, the biggest one is in the last array element. I know that if the thing I found is equal to the value I want, then I found it. But if the thing I found is bigger than the thing I'm looking for, then I haven't found it, if that makes sense. So does what I'm saying down here make sense? I know that if I found the element that I'm looking for, like if I'm looking for the number 6 and array x is the number 6, then I found element 6, so I'm all good. I know I found it. But if I'm looking for I'm looking for the value 6 and I find the number 9 in this array index, then I know that I haven't found the 6 up until now, and this one's bigger than the 6, so I can stop looking. It's definitely not in here. Cool. So let me improve this code. This may or may not be improved. I'll just leave it as gross small protons. I am unsure why it is so slow, because it's on my phone and my phone should be fast. And my phone is on 4G, so it's... Cool. So does this make sense? I know that if the thing I'm looking for is in this array element, then I found it. I know that if the array element is bigger than the thing I'm looking for, then I haven't found it. It's not going to be in there. And otherwise, I'll keep going to the end, and then I'll discover that it's not in there. Cool. So how much faster is this going to be? Is this going to be faster? Is this going to be at all faster in any way? Yes, one person's nodding. I would hope that it would be faster in some way, otherwise I've just wasted my time. Compile. Okay, and I need to give it a sorted array. Okay, that is approximately 10 numbers. Cool, it compiled. Clearly, my code is not broken. Is VLab this slow for you guys normally when you're using it, like at home and stuff? Who finds VLab this slow normally? Wow. I'm so sorry, it's not this slow for me at home, and I have shitty internet, so that's terrible. I feel your pain now. So if I'm looking in my array now, right, my array is in sorted order, so smallest through to biggest. So if I'm looking for the number 5, right, I look at the array elements 1, 3, 4, 6, and then I go, it's not in the array. So I only have to look through the elements up until, up until this one here. And then at this point I can go, okay, cool, I know that it's not in here because I found something that's bigger than me, so I can stop. Cool. So is this all good thus far? I've made a slight change which will make it slightly faster. But this still isn't going to be super great, because what if the number's at the very end? Or what if it's not in there at all? Like, I'd have to keep on searching and searching. And I've still got to look through every single element up until a certain point when I can stop. Is there any sort of crazy hack that I could do to avoid having to look through so many things? So I have a question. How many of you have used a phone book before? How many of you know what a phone book is? Okay. There will come a day when that is not true. So do you have address books, physical address books? I bet you don't, because you have phones and computers. So if you imagine we have this strange, big, massive log of, chunk of paper that's like 1,000 pages thick, and it has everybody's name and phone number for some reason, because for some reason we can't just find people's phone number out by Googling them. And so it's sorted from A to Z, right? So the top of the book, the first pages have A, the last pages have Z. If you were trying to see if I was in there, so B for Bennett, what would you do? Would you start at page 1 and go, nope, and page 2 and go, nope? Or is there like a better approach that you could take? Any ideas? Yeah.
Go to the page or the section where the letters for your name are.
Yes, you'd go to the section with the B's in it. How would you find the section with the B's? Index page is a good idea. What if there's no index page? Have any of you had this problem before? Like you've had to, I'm feeling so old all of a sudden. Gosh. So if you have an index page, right, you can go, oh, the Bennetts are going to be on this page 50, so I'll go to page 50. But if you don't have that, what could you do? Yeah? Yeah, that's a reasonable answer. Open randomly where you think the B's will be. I think the B's will be about here in the book. And then if they're not at that point, what do? Yeah, try again. Do you try again at random, or do you sort of narrow it down? Yeah, you narrow it down, right? So if you are looking for a last name starting with, I'm bad at letters, like L, for example, you'd sort of open towards the middle and hope there's M's there. Then you go, oh, it's smaller than M's. You'd sort of open about halfway back along the phone book and go, oh, this is like the J's, kind of halfway between those, and then you sort of go until you found the right point. So conceptually, does that make sense? I can't believe I have to explain how to look up in a physical phone book. But do you understand what I'm saying? Like you can sort of divide it in half. So take the phone book and go, is it in the first half? Yes, it is. Like it's smaller than M. I've opened to the M section, so it's going to be in there. So I can ignore all of the stuff that's bigger than M. So then looking in the A to M section, guess about the middle will be like J or something. It's not before J, like L is after J, so I can ignore all this stuff at the start, and I can just look in this section that I've narrowed down here. And so on. So does that make sense? If I have my phone book going from A to Z, and I'm looking for, looking for L. So if I open in the middle, that'll be roughly about the M's. And so I know that because the last time I'm looking for starts with L, it's not going to be in this half here. Right? Does that make sense? So I never have to search in any of the things in this half, because I know for sure that I'm not going to find them in there. I know that L is smaller than M, right? And so I've instantly, I've narrowed down, I've eliminated half of the stuff that I have to look for. So I no longer have to look through half of this phone book. And then I'm looking for L and that's not M, so I'd sort of go, okay, well somewhere around here is like J, maybe. So I'd sort of, open a chunk in the middle of the half that I've narrowed it down to, I'd go, oh, this starts with J, right? So I know that it's not going to be in the first half of this. I know that L is going to be bigger than J but less than M, so I now don't have to look at this chunk either. And so I can keep on doing that, I can keep on narrowing it down. I sort of pick a halfway point in here. That might be like K. L, that might be L. That would be good. So I go, oh cool, I found the halfway point, this is L, and I'd sort of flip around the next couple of pages to find the right thing. But do you see what I've done here? I've been able to sort of make jumps. Come on. So rather than having to look here, and then here, and then here, and then here, and here, and so on, I was able to jump around. I was able to go, okay, I'll look in the middle at M. It's not there. I'll look in the middle at J. It's not there. I'll look in the middle at L, like the middle of those two middles. And so I found it in pretty much like 3-ish steps, which is a lot better than searching through the entire alphabet. So does this sort of idea make sense conceptually? I can narrow down the range that I need to search in because I know that if I'm looking for a last name starting with L, it's not going to be between the M to Z section. Cool. So do you reckon taking a, drawing a parallel back to the array stuff we're doing, could we use this somehow to search through an array to find a thing we're looking for? Yes? Yes? One person's nodding. I sure hope we can. And so we call this a binary search. It turns out, actually, yes, this is a thing we can do. It's a very common thing to do. Oh, look. I'd forgotten that was even in the slides. But that button. We call this a binary search because we're splitting it in 2 every time. So each time we're sort of eliminating half of the possible things to look at. And binary is like 2 zeros and 1s. So the code here is a bit confusing. And I don't know if this code is correct because every single binary search code that you've ever found will be broken. There's a really good story here, and I've forgotten what it is, which is unfortunate. But there's sort of it's very, very hard to get this code right, and even the implementations in textbooks and stuff are normally broken and have bugs. This is Andrew Taylor's code, so I'm not sure what the bug is going to be in here. Maybe I'll find it out. But if I sort of walk through this code, cool. So walking through this code and sort of explaining what it does. If this is my array here, so like these are the numbers, 1, 2, 3, 4 through to like, I don't know, 30, 40, bigger numbers on this side. I start out by saying, okay, the range of things that I'm going to consider. I'm going to consider everything in the array, so all the way from the start to the end, right? All I know right now, I haven't started, I know that it's somewhere in this array. So then I'm going to take the middle point of the array and go, okay, what number's in the middle of the array? And so that's what this code here is doing. The middle of the array is going to be like you add the top and bottom. You go, if I'm searching between elements 0 and 100, then the middle is going to be 50. So you look in this array element 50. If it's the thing you want, then cool, you found the thing you want, awesome. It's there, you found it. Otherwise, if this is bigger than the thing you're looking for, so if we're looking for the number 20, say, and this has got a 50 in it, then we know that it's not going to be in this bigger half. So we update our bigger one, like our end range, to be that middle point, and then our start range will stay the same. And so then we look again in the middle of these 2 points, so we go, okay, well, let's check in the middle here. If this is the number we want, cool, we found it. But let's say we're looking for the number 10, and let's say this is a 20. We know that, let's say we're looking for the number, what did I say was here before? This one can be 20. Let's say we're looking for the number 15, and so this element here was a 10. The thing I want is between 10 and 20, so I know that it's not going to be in this section here. So now my new start becomes this spot here. I did not mean to push that button. Oh well. But does that make sense? You keep on you go, I know it's going to be within this part of the array. When you put you sort of split that in half, and then if you know it's going to be in the bottom half, it's in the bottom half. If it's going to be in the top half, it's going to be the top half. You change that to be the range that you're searching through, and then you keep on going until you hit the point where you've found the thing, or where you've found that it's not there because you've hit the middle point, like your start and end and middle are all at the same place. Cool, does that make sense? Any questions about that? If anyone's sitting there bored and thinking they know all the stuff already, find the bug in this code, because there's probably going to be a bug in this code. Like even the one correct implementation that was written, like some guy looked through, he bought a whole bunch of textbooks for all of the computing textbooks and looked at all of the binary searches, and they were all wrong. And so he wrote the version that was correct, and he went, cool, this one I've worked out, proven it's correct. And then 20 years later, he was like, oh, there's a bug in this. So try and find the bug if you are sitting there bored. Otherwise, let's this one, yeah, let's put this into the VLab. Oh no, okay, it hasn't crashed, cool. Cool. Cool, and so I've got this code, I've told it to print out the thing that it's looking at. So, compiles, runs. So if I'm looking for 5, in my array here like this, I jump to the middle, which was about the 8. Let me move that across. I went, 5 is smaller than 8, so I then jumped to looking in the range of this 1 to 8. The middle of that was like 3, I went, is it the 3? It's bigger than the 3, so I'm looking between the 3 and the 8. Is it the 4? No, it's bigger than the 4. Is it the 6? No, it's smaller than the 6. So because I've hit this point where I know it's would have to be between these two, but I haven't found it, then I know that it's not in the array. If I was, no. So if I'm looking to see if the 8 is in the thing, I find it in one guess, right? If I'm looking to see if the 8 is in it when I search through the normal way, I have to look at all the things before the 8. So this is pretty cool. 1 step versus 5 steps doesn't really make a difference when you've got 10 items, right? But if you had like 1,000,000 items, then it would make a difference. So I might try and, in the break, I'll try and put a thing together that will have 1,000,000 items so you can see the difference in speed. But then the question is, okay, here we've got some code, it looks faster, it takes fewer steps. How do we work out how fast it is? Right? And so if we look at the operations, right, so in the linear search, we had to search through every single element in turn. So we had to look at, you know, in the worst case, every single element. So if there are n things in our array, we have to look through n things in the worst case. With this one here, we're splitting it in half each time, right? And so if we're splitting it in half each time, does anyone know like what the mathematical equation would be for the number of times you can split something in half? Take the first letter off and say the other ones. Yes. So we'd call this log of n, or log base 2 of n, is the number of times that you can split an array in half of n items. So in the best case, we find it in the first check, right, just like before. But in the worst case, because we're splitting it in half each time, we never have to look through everything. At the most, we have to look through what we'd call log of n, which is, what's a logarithm mathematically? I don't know how to describe that. Let me draw a super quick picture to explain what I mean by this, because painting. Cool. So one way you can think about it, right? If this is our array, then the next time we search through it, we're going to be searching through either this half or this half, right? We'll only be looking in one of these two halves because we've narrowed it down to that. And then the next time, we'll have narrowed it down to one of the quarters. So we'll only be looking at one of those possible things. And then the next time, let's say that these are now individual elements. So when we're actually looking at this, we'll have to look and see if it's in this one. And then, like, say we've narrowed it down to this range, we've narrowed it down to this range, we've found it here. So in the worst case with this one, we're going to have the 4 steps. And log base 2 of this width is 4. Screen. Cool. And so log of n grows very slowly, right? So log base 2 of 10 is about 3. But then log base 2 of 1,000 is like 10. So if we had 1,000 things to search through, we'd only have to take 10 steps. If we have, is it 1,000,000? If we had 1,000,000 things, and we're splitting it in half each time, we'd only have to do 20 things to look through. If we have, I don't even know how many zeros there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What is that number called? 1,000 billion? A gazillion, maybe? But even if we have 1,000 billion things, to look through all of them dividing in half each time is only 40 checks. Right? So apparently there are 10 to the 80 atoms in the universe. To look through every single atom in the universe with a binary search would take 240 steps. Like, dividing in half and half and half each time is very powerful because each time you split in half the number of things you have to look at. So even if you have the whole number of atoms in the universe, you can, if they're in sorted order, you can search through them to find the right one in 240 steps, and that's it. And so if that was done in an array in a computer, that would be less than 1 microsecond. Good luck getting all the atoms in the universe into an array. So this is a good place to take a break. Okay, hello again, everybody. I hope you had a good break. Hello, everybody. I hope you had a good break. That's basically it. So let's look at something new, or something different to that. So I had someone ask me in the break a really good question along the lines of, if the input isn't sorted, if we have an array and it's not sorted, and we sort it first and then do a binary search, is that a good idea? Should we sort it first and then binary search? And the answer to that, it sort of depends on what you're doing, right? If you want to look through your array lots and lots and lots of times, you want to search for many, many different things. If you start out by sorting your array once, then it's in sorted order, and then you can do this binary search thing to really quickly find things in it. And so, in order to do that, you must know how to sort things. When I say sort, when we talk about sorting, we mean to rearrange the contents of an array or any sequence so that it is in non-decreasing order. So things are either equal to or bigger than as they go along. And it's useful to do this, if we have something that's sorted, we can search through it much more efficiently, like we've just seen. The downside to doing this, the downside to something like this, if you want to search through an array, right, and so you sort the array and then you do a binary search, sorting the array is going to take longer than just looking at everything once anyway. So it would have been more efficient to just look at the things once. And if you sort it using a simple, obvious algorithm, which is sort of intuitive to understand but really slow, then that's not going to be very fast. There are lots and lots and lots and lots of different sorting algorithms. It's a very kind of active research area, I guess, very interesting thing. But we're going to look at just 2 of them in this course. So one that's sort of a really slow one called bubble sort, and one that's a very fast one called quick sort. It's not actually all that quick. Thank you, tutors. So, how many of you have heard of bubble sort before? Okay, quite a few of you. So, the idea with bubble sort, we have an array, and we want to sort the array. We go through the array, we look at every pair of elements. We look at the element and the one after it, and so on and so on. If they're not in order, like if they're in the wrong order, we swap them, and then we just keep on doing this until the array is sorted. So I made this beautiful example here, if you can read that. Like if our array starts out at 31495, first we would compare the 3 and the 1. They're in the wrong order, like it should be 1, 3, not 3, 1, so we swap them over. So now it's going to be 1, 3, 4, 9, 5. We move on, compare the 3 and the 4. Those are in order, that's fine. We move on, compare the 4 and the 9, that's fine. We compare the 9 and the 5, that's in the wrong order, so we swap them. And then we're at the end and it's sorted. Saying words and like waving my hands around at this is limited in how useful it can be. And as such, I require some volunteers. Would anybody like to volunteer to hold a number?
We're counting on you.
I don't know if you heard that terrible joke up the back. Okay, can I have some volunteers? Come down, please. I don't have to pick you, you can just come down. Yes, you should come down. I have up to 20 pieces of paper, I think. So anything up to 20 people.
Hello, do we get to pick numbers?
Cool, yeah, sure. Which number would you like?
3.
There you go.
Thank you.
I don't know where 1 is, you can be 2. Would you like to be... Cool, I need some more volunteers. Come on down. Cool, any more volunteers than this? Would you like to be...
Next.
Okay, hopefully this is enough people. So make sure you're not standing in sorted order for a start. Cool, it's looking good. So if you hold up your numbers, I think I have enough volunteers, I'm sorry. I think I have enough volunteers because I don't want to be doing a very slow sort on this many more people. So if you hold up your numbers, people at the back, can you see their numbers? Yes? No? Cool. So I need 1 more volunteer. Someone can be a 6, someone can be a 9, just decide in advance, it'll be fine. I need 1 more volunteer who's going to actually do the bubble sort. So they're going to point at the people and say, you should swap with you. Are there any volunteers for this? Are you volunteering? Cool. Hello. What is your name? Jonathan?
Yeah.
Hello, Jonathan. So, do you think you're a pro at quicksort? At bubble sort? Bubble sort's the one we're doing here. Cool. So, to do a bubble sort, you need to compare every pair of people, right? So, if you start out looking at these first 2 lovely people, what's your number?
3.
Should they swap? Yes. Cool. Cool, so looking at this first sort of run through we've done, what have you noticed? Yeah, the 19 has gone all the way to the very end. The biggest number has gone all the way to the very end. Cool, do we need to keep going? Is this sorted now?
Not sorted yet.
It's not sorted, cool, so keep going. What are you going to do next? We should be counting how many times. We've already done, how many of you are there? There's 15 of you. So we've already had to compare 15 people. 16, 17, 18, 19, 20, 21, 22, 23. Okay, so you've compared 24 people so far. Keep counting the number of people you compare. I think you're at 24 so far. Cool, so we're at 28 if I counted correctly at the start.
Yeah.
Cool. How are we going? Is that sorted now? Almost. Cool. Are you all in sorted order now? Nope. Cool. Okay. Could you read out your numbers, people with numbers?
2, 3,
6,
7,
8,
9, 10, 11, 12, 13,
Seems sorted to me. Good work. So I have another demonstration to do of a different sorting algorithm. Do you want to do the demonstration of the second one now and then code for them both? Or do you want to do second demonstration? Okay. So we have another algorithm. I'm just going to turn the lights off for a second so that you can see the slides. A quicker algorithm called quicksort. And the idea behind quicksort is that it does sort of a similar thing to binary search. It tries to make the problem smaller each time. And so it does this by, basically, it takes the array, it divides it into two smaller arrays, and then each of those into two smaller arrays, and so on and so on. The way that this works is it chooses a pivot, so like one of the elements of the array as a thing called a pivot. And then everything that's smaller than that, it will move to the left, and everything that's bigger than that, it will move to the right. And you'll notice then, so they won't be in sorted order at that point, it'll just be that this person is in the middle, everyone here is smaller but not sorted, and bigger but not sorted. But then we can compare this half here. Pick another pivot there, move everybody so that they're smaller and bigger on one side and the other side. Do the same for this one, and so on and so on, and then things will be great. Jonathan, do you think you're up for doing that? We'll give it a shot. Do you want to shuffle yourselves so that you're not in sorted order? Cool, they look sufficiently shuffled. So, do you want, I'll talk you through what to do and then you can do it. Does that sound good? So we pick somebody as the pivot. So what's your name? Andrew. Andrew? Good name. Andrew is going to be the pivot. And so now we want to get everybody who's smaller than Andrew to go on this side and everybody who's bigger than Andrew to go on that side or to stay on that side. Does that make sense? Yep, so go through the people. So what number do you have?
11.
Cool, so 11 is smaller, so it should come on this side. Yep, 7 is smaller, so go over. 13 is bigger, so stay on that side. And you want to sort of move along as you do this so that you'll not all fall over. So don't sort yourselves, stay in the order that you were in before. But just moved around. You sorted yourselves.
Did we?
You did.
I think that's just a coincidence.
You should...
It's just like sending them to the back.
Okay. As long as you're being consistent. Okay, if you're going to the side, yes, I'm happy with that. I'm satisfied. Cool, so where was Andrew? Where are you standing now? Cool, number 12. So we now know that everything on this side of Andrew is smaller than 12, and everything on that side is bigger than 12. So now we've made two problems that are smaller problems. Sort this half and sort that half. So do you want to move down a little bit so that you can all sort of see each other still? So shall we start with the people on this half? So pick someone else to be a pivot. What's your name?
Kevin.
Kevin? So Kevin can be our pivot for this one. So now you go through up until you get to Andrew, and then stop. Cool, so the pivot is 10, 8 is smaller than 10, so it goes to this side. Cool, do you want to keep walking down? Cool, and so now we know that, was it Kevin? Kevin, everybody to the left of Kevin is going to be smaller than Kevin, everybody to the right is bigger. Is there anybody to your right? Just one person. Cool. So now we've made ourselves two smaller problems, sort everybody to the left and sort everybody to the right. So if we sort everybody who's to the left, pick another pivot. What's your name?
Victor.
Victor, cool, so Victor is your pivot, so. Who was your pivot? Was it? Okay, 10, cool. So now we have made a smaller problem of these people and those people. I feel like you're not picking very good pivots because you're only having one person, but that's fine. So pick our next pivot. What's your name?
Felix.
Felix, cool.
Choose the smallest number.
Actually, those of you who are pivots, can you sit down? Or do something like just where you are so we can see that you're done? You can sit down more comfortably if you want. So we know that these people are the pivots and they're done, so we can easily see. So you are also a pivot, you're also done. So then the remaining array we have between these two pivots here. New pivot. Cool, and so now our new pivot is done, so you can sit down as well. We now need to sort like the other half of this array that we had, which has one remaining person. So this is our pivot, they are now done. Cool, so then the next free one was the 8, they're done. Cool. This element, the array with the 11 just has one thing, so that's done. And so now we're doing this on like the second half of the original array we had. So cool. Do you want to read out your numbers?
2,
3,
6, 7,
8, 9, 10, 11, 12, 13, 14.
Sounds pretty sorted. Good work. Are you satisfied with those demonstrations? The bubble sort seemed faster. The bubble sort is not going to be faster if we're a computer as opposed to people who are confused. And if you imagine if I tried to sort the entire lecture theatre, right, if I had to go through every single pair of people, like if there are 500 of you, how many pairs would there be? There'd be like 499 pairs, right? Because there's everybody divided in that. But then if I have to go through all of you every single time and then again and again and again and again, right, that's going to be, the 500 people will make roughly 500 pairs. Then I've got to go through each of those roughly 500 times. So that's 2,500 times, which is a lot. Whereas if I'm doing a quick sort of the room, each time I pick a pivot, I move everybody who's smaller to the left and bigger to the right. And now I've divided it in half. So then I take my next, my first half, pick a pivot, move everybody who's bigger and smaller and so on. Moving you around the lecture theatre would be annoying and take a lot of time because you'd have to coordinate and walk around. But can you see the dividing in half thing each time means that if we pick a really good pivot and we do split the list in half each time, it will take much less time? Is anybody convinced? Cool. All right, well, thank you, volunteers. If you would like to keep your numbers, then I guess you can. Otherwise, put them down here. But yes, thank you for your... Cool, and so I have this really cool visualization thing here. Cool, that's all good. So I think that if I hit run, this will do the thing. Cool, so this is like a visualization tool that one of my students from some number of years ago has put together. And so currently it's doing a bubble sort, and so you can see it's going through and comparing every single pair of numbers together. And you can sort of see by the time it hits the end, the biggest number is now in the right place. And then it's got to go through, as it goes through the array or the list or the bars or whatever you want to call it, each time the very biggest one will end up at the end, like in its spot. So you can sort of see that's going to happen here. I wonder if I can speed it up. I can, but then it breaks. I guess this is a good lesson about parallelization. If you try and do too many things too quickly, then you... That's roughly spelled right. Does this one have quicksort and bubble sort? Do you know? I'm going to try and jump to the sorts that I'm meant to be showing you. Okay, this has music. Oh, sounds. And that is not muted. Cool. So here is an example of quicksort. You can see it's like sorted one half, and then it goes and splits that into halves, sorts each half. This is not quicksort, this is one called merge sort, but you can see it's doing a similar sort of splitting in half thing. It's so great. Let me see if I can find... Do you want to keep watching all of them rather than... Yeah. I don't blame you. So this one is called heap sort. Heaps are a really cool data structure that you'll learn about in COMP1511. It's basically sort of like an array, but when you add it to the array, it becomes sorted. So you just go through and add the things to this heap, like a data structure of some kind, and they just get added in sorted order. Whoosh. Radix sort is very complicated. This is this sort of magical sort in that it sorts things by their first digit, and so it'll group all of like the 10s on one side and all of the 20s and so on, and then it can go through and do it much faster. So this is the sorting algorithm that's used by the GCC compiler. It's the one that's built into C. Works like this. You can see it's almost sorted everything. It's very close to sorted, then it goes through and does one final pass and does the little ironing out the bumps. Okay, so this is a similar sort, but it's a stable sort. So one thing worth noting when you're sorting things is, do they stay, like the ties stay in the same order? So if you can imagine, if I'm sorting a deck of cards, right, and I'm sorting by the number, will like the two aces of different suits stay in the same or respective order? So this one tries really hard to, or succeeds at not swapping things that are the same. This one is shell sort. It's a very complicated algorithm that yeah. Okay, here's bubble sort. You can see there's heaps fewer things because they didn't want to have you sitting here for 10 minutes just watching bubble sort. So you can see it's like less than half as many things. Each time it's going through, and the thing that it moves up becomes in that position, if that makes sense. What do we have next? Cocktail shaker sort is bubble sort, but you go in both directions. So you move this, the biggest one up and then the smallest one back down. It's very cool. I have never heard of gnome sort before. Bitonic sort? This is pretty cool. BOGO sort. So the way that BOGO sort works is that it randomly swaps elements and then checks if it's sorted. So it doesn't make any progress, it doesn't improve on its previous one, it just keeps swapping them at random until they happen to be sorted. I think maybe they give up at some point. As you can see, it's useful for your sorting algorithm to make progress. So when it's made one operation, it's closer to being sorted. This one does not do that. There are a lot of really fun videos of sorting algorithms, and I recommend just sit around with your friends watching them because they are actually really great. I might show you the two at the start that I skipped over as well, just as a good example. So these ones also have the wider bars because it's a slower sort, and so it doesn't want to have it take quite as long. Let me go back and describe it. So selection sort picks the thing that should go in the right place and puts it in there. So from the remaining array things that aren't sorted, puts which one should go next. Insertion sort is the same but different. It goes where should this next element go within the things that we have right now. As you can see, it sort of goes along like a mountain of becoming sorted. You can see it goes through everything in the array over and over and over again lots of times. So it's not like breaking the problem down and making it smaller. It's always going through everything. Whoosh. And then quick sort in comparison. Look at how tiny the bars are, right? Like it can sort so many more things. And you can see it's splitting the problem in half each time. Each time it's doing less work. And so it's never sort of going through the whole thing again and again and again. It's sort of going, just doing this bit, this bit, this bit, and so on. And then let's grab bubble sort again. Bubble sort was next. Yeah. And so you can see bubble sort, it's going through everything in the array over and over and over again, right? It's not doing anything to like split the problem in half and make it easier. Every time it's sort of going, what's the next thing that I should put here? Like it's looking through all of the things every time. So based on these beautiful videos and fantastic sounding videos, Can you sort of see what I mean about how quicksort is a lot faster because it breaks the problem down each time? It goes, this whole thing is hard to solve. You know, here's the half that's bigger than this, or that's smaller than this, bigger than this. Solve those each independently. Whereas bubble sort doesn't have any sort of clever split in half sort of thing. It just goes, I'm going to keep sorting the things in a loop. Very fun. There's so many of them on YouTube. I'm going to close this before I look at any more. So let's look at the code for bubble sort then. The lights are off, cool. So the code it's fairly straightforward, right? You loop through. Exciting videos are over. Hold on your excitement now. You effectively bubble sort loops through the array over and over and over again until it's sorted everything. And each time it goes through the array, it's asking itself. It looks at like this element and then the one right next to it, and it goes, are these, like, should these be swapped? Are they in the wrong order? If they are in the wrong order, then it swaps them. So it does this by making a temporary variable to hold on to the first one, makes that be equal to the second one, and then copies the temporary one. And so then each time it's going to go through swapping things and swapping things and swapping things and swapping things until it hits the point where it doesn't swap anything. So within the loop, we set out by saying, like, swap is 0. We haven't swapped anything. If we swap something, we then set this variable here saying we have swapped something. And so the loop will just loop over and over and over and over and over again until it has no longer swapped something. So does that make sense? The way that the code works, it just goes through, it looks at every pair of elements going across and swaps them if they're out of place. Would you like to see this code run? Yes? Cool. You don't have to just believe me that it works, you can actually see that it works. So I'm just going to write some code that will scan an array from standard input, so I can just give it a whole bunch of numbers. Print array, bubble sort, and then print array. Cool. Ah. I think this one, Jishank, what's the Unix command to generate random numbers? Ah, very good. Cool, so I've run the seq command to generate a sequence of numbers, but the numbers are between like in sorted order. So I've piped it into the Linux sort command with the randomized thing, so saying randomize them rather than sorting them. Cool, and then I will put this input, come on, to my bubble sort. I think that's still valid code. Cool, let me, oh, I just don't print any new lines, I see. Come on. Cool, so there you go. You can see it's given these numbers here. There's 100 of them, and then it prints them out in sorted order. But that's kind of boring. That's a small number, so let's make it be a big number. Let's make it be 100,000 instead. Cool, and that was a really big mistake. Oh, there we go. It is actually sorting them at a reasonable speed. Oh no, that's just printing out the array. And now it's going to sort them. Yeah, so that number was probably a huge mistake. If you think about the math, right? If I have an array with 100,000 things in it, and bubble sort goes through everything in the array over and over again, right? It'll go through it approximately. Is that viewable over that? Cool. If our array is, nope, reg. So if this is our array, pretend that there are, elements in it like this. If this is 100,000 big, and it goes through every array element, sort of the number of array element times there are. So it's going to go through this 100,000 times to put the first one in the right place. And then it'll go through 99999 times to put the next one into place and so on. So it's going to have to go through it approximately like the number of things times the number of things. So what is 100,000 squared? Do I just add the zeros together? That's a lot of zeros. Maybe let's not run it on that many things. Right, I got to do that thing. And it's going to tell me where it got up to. There we go. I was up to 67,000. It had swapped something. I'll get it to scan in a size, and then do that size instead. Okay. I'm trying to work out how I can tell it how many things, but I've just realized I can use argv, and then I won't have to worry about how to do this. There was a question the other day, when do you use char argv? So when do you use void and when do you use argc-argv? If you want to use command line arguments, so if you want to be able to say /bubble and then some number for it to read in, that's when you would use argc-argv because you want to get the command line arguments. Size equals a to I, argv. I'm just going to say if argc is less than 2, return 1, otherwise you will try and read a size that is not there. It might still work. Okay. Okay. Cool. So this is going to give it 1,000 random numbers as input, and then also give it the command line argument 1,000, which it will use to know that there are 1,000 things. And so you can see that was almost instantaneous. But if I make it be 10,000, it's also still pretty instantaneous. I've put the time command in front, so it's going to time how long it takes to do this. So it took about 1 second for 10,000. If it took about 1 second for 10,000, how long will it take for 50,000? It'll be a lot more. Let's make a smaller number. Okay, let's leave that, there we go. So to do to 25,000, it took it 10 seconds. So I'll get it to do 50,000 and then we can move on to something else while it does that. Cool. So that can sit there and be slow. Cool. So does bubble sort make sense? You feeling sort of comfortable with that? You go through every pair of things. If the pair is not in the right order, swap them. And continue doing this until you have no longer swapped them. And this will work, it will sort things, but if you have a gazillion things, it will be very slow. And then quicksort works by dividing things in half each time. So it goes, everything on this side is small, everything on this side is bigger, and then does the same thing for each of those. The code for this, and again, this is not my code, so apologies. But it's doing what's called like a recursive algorithm. I'm not sure if I've talked about recursion. Have we talked about recursion here? Not really. So recursion is what we call it when a function calls itself. So we can see here the quicksort1 function is calling the quicksort1 function inside itself. And so it's going to call itself some number of times until it hits a point where it should stop. If you don't have some way of saying if this happens then stop running, then it will just run forever. So in this case, the way that it works, you give it the array and the low and the high point. So like, if this is the whole array, you are currently considering the part of the array that's between 1 and 10, for example. You then partition the array, which is the thing that will do the shuffling, which is down here. This will take that pivot and then sort all the things on either side of it. Let me try that again. That will take the pivot and then move all the things onto either side of the pivot based on if they're smaller or bigger. Okay, so this is working by going from both sides. This will also need a picture. So the way this works, you saw when we had the people up here, we could just move the people along, right? So we could say, move along that way. That does not work with an array. You can't tell the array, oh, just move along that way, it'll be fine. And so then the way that this partition thing here works, let's say this is our array, right? So each of these is a number, a field in the array. It picks the pivot value to be the one that's in the exact middle. So let's say that's the middle one, for example. Maybe that's got the value 10. And then it goes along from both sides until it finds something that needs swapping and then swaps them. So for example, if this one, that's a 2, that's smaller, that's a 20, that's bigger, it'll go along here, it'll go 2 is smaller than 10, it's in the right place. This 20 is bigger than 10, so it needs to go into the other side of the 10. And then it will also look backwards from the end of the array until it finds something that's smaller than the 10, so like a 5. And then it will swap them over. So that would become the 5, that would become the 20. So does that make sense? Rather than trying to move people around the stage, it looks from either sides until it finds something that needs to be swapped, and then swaps them. And then it'll keep doing that until it has moved the things along. So it's going to effectively go through everything once, go into the middle until it's hit the pivot again. And so when this function has finished running, your array will now be, the elements will be moved around such that the thing in the middle is the pivot in the right place, and then everything on the left is smaller and the right is bigger. Turn off. And so then the quicksort code works by going, start out by partitioning it, so pick a pivot in the middle, move everything on either side of it, and then do quicksort on the bottom half of the array and the top half of the array. Right, so it's, elegant, simple code. It says, do the partition thing, so like, pick the person in the middle, move people on to the left and right as they're smaller and bigger, and then now call quicksort on the bigger half of the array and the smaller half of the array. Does that make sense? The code is sort of very simple, very complicated if you don't understand it. I was not paying attention to the time. It is now 3:54. Okay. Are there any questions before we pack up? I guess a question that you might have is like, do I need to know this for the exam? The answer is I don't know. I think that you won't be asked to implement these. I'm fairly certain that you won't be asked to implement them, to write the code for them, but Andrew Taylor will get back to me on that one. But you should have sort of an understanding of the concept that, right, let me talk for like 30 more seconds. You should understand the concept that you can do the same thing in ways that are faster and slower. So for example, you can sort things using a bubble sort, which is actually quite slow. You can sort them using a quick sort, which is quite fast. You can see here